Hi everyone, and welcome to the last video on our equilibrium packet. I have a cat hat, and I have a cat hat for a reason, at least a good reason in my head. Today's topic for this class is Le Chatelier's principle, and if you've ever taken French, Le Chat is the cat. So I get a cat hat, some cat paws. Cat irons are positive. I got a cat hat and some cat paws to talk about Le Chatelier's principle in my brain, and it's one of those weird things that might help you remember it and might not, but it's what I think of. It looks to me like a combination of the words cat in French and chandelier. If you've got a chandelier and you've got a cat on one side, you've got a problem because you have a crooked chandelier. I don't have a chandelier or a cat, but I imagine that the chandelier would be tipped at an angle because of the weight of the cat. So if you can't get your cat down and you want your chandelier to hang correctly, you need to add weight to the other side. You need to fix the equilibrium by changing your balance. And that's what Le Chatelier's principle says. If you have an equilibrium reaction and you add something to one side of it, the reaction goes the other direction to fix itself, to re-achieve equilibrium and to re-achieve balance. So I have a 10-pound cat on one side of my chandelier that won't come down. Oh, easy. I hang a 10-pound weight on the other side. Just pretend the cat's not up there because I really don't need it now anyway, and go about my business. 3 ways you can disrupt a chemical equilibrium. Add or remove a reactant or product. If I hang the 10-pound weight and then the cat jumps down, I need to fix the chandelier again. If I have a reaction that has gas molecules in it, changing pressure by changing volume will shift the equilibrium, and changing a temperature can as well. We'll be looking at that with exothermic and endothermic reactions. So the first thing we're going to look at is your very basic reaction, A plus B yields C plus D. It's in your packet. So what you got to know is if I'm adding A or B, I'm going to make more C and D. If I'm adding C and D, it goes the other direction to make more A and B. So whichever side I add to, more of the other side is made to fix it. It pushes away. So if I add a substance, then it needs to be removed. So if I add A, we go that way. But if I were to take away A or B, more would be made, and the reaction would proceed that way. So if you look at your examples, for the reaction, A plus B yields C plus D. If D is added, I move away from where it's added. I make the reactants as it's written. If A is added, I'm making products as it's written. I'm shifting right away from it. And if B is removed, I'm bringing the reaction to the left to make up for the B that has been removed. For volume and pressure changes, if I've got liquids and solids, no one cares. What we're looking at with gas phase reactions, though, are your number of moles per side. That's what you got to care about. Because remember, it doesn't matter what kind of gas it is, 1 mole, 22.4 liters, standard temperature and pressure, whether it's helium or sulfur hexafluoride, we don't care. On this side, I've got 3 moles of gas. On this side, I've got solamente uno, only 1 mole of gas. So, under conditions of higher pressure, if I increase the pressure, I'll make EF2, where there's only 1 mole. If I were to decrease the pressure by increasing the volume, so less pressure, I'm going to tend to make where I have more moles of. So you can still do your classic shifts if you're on your example here. If E is added, I'm going to make EF2. If EF2 is added, I'll make E and F. So far, so good. If F is removed, I'm going to go left and make E and F to get more of it. The volume is decreased. So I'm going to squash this. It is way better to be 1 mole than 3 mole if your volume is decreasing. So if the volume decreases, I'm going right toward the side with less moles. One more thing to do, temperature changes. For this one, the big thing is to remember that in an endothermic reaction, heat is a reactant. Heat is absorbed to make products. In an exothermic reaction, heat is a product. It's given off. And then you do your classic Le Chatelier's balance thing. So if I were to add heat to an endothermic reaction, I'm adding a reactant and product is made. If I'm adding heat to an exothermic reaction, it's a product. Reactants will be made. That's your shift. So, if I'm heating, like it says, heating an endothermic reaction shifts right. Heat is a reactant. An increase in T will increase K. And an increase in T decreases K for an exothermic reaction. Check that out. It's going to be strange to think of that where an increase in temperature is going to decrease your K with your exothermic reaction, but it comes from heat as a product. That's more something to remember. I always work through it stepwise with write them out, think of where heat is, and work through that. A catalyst, I had to. What effect does a catalyst have on a reaction? Well, it makes it go faster, decreases your reaction rate. You're going to change your activation energy, not your equilibrium. It just makes it happen more quickly. So that's the summary of equilibrium and Le Chatelier's principle. When I looked up the notes for this, looked up some info, I found the chart that's on the last page. It's pretty nice. If you just remember that whatever change occurs to the reaction wants to re-achieve its balance, so it goes the opposite direction. It fixes whatever you've changed. You'll remember Le Chatelier's principle. Keep your eyes out for exothermic, endothermic, and gas phase reactions, as I don't want to call them exceptions, but special cases with more to consider. So that's my last lecture for equilibrium. We'll be getting ready for our quiz soon, and have a great day.